Okay, good afternoon. Let's start lecture. Okay. So 2 more lectures left, and then we'll finish the welded joint today, and then get started with the spring, which is the last part of the course, or the machine component. We could finish maybe majority part of spring today, and a little bit using next lecture, and then next lecture I'll do some quick reviews. Okay. So, and that should be it. Then I'll see a little bit about a final exam in the next lecture. Okay, yeah. Just a quick review on the welded joints. Okay, so we looked at basically the welding symbols, specifications, and how to interpret a welding symbol. Okay, how to map the symbol to appropriate the type of welding you're looking at. Now the focus of the weld is going to be on the fillet weld. So we're going to look at basically the safety of a fillet weld. In order to do that, we need to do 2 things. One thing is what's the stress in the fillet weld, and what will be the strains for that, right? Yeah. So for the stress, and we look at the 2 different approaches. One is the so-called analytical approach, basically to analytically derive the maximum value for a stress inside the fillet weld. But we also show that basically experimental saying is analytical value cannot describe the actual stress all the time. So then what we do is we use a so-called conservative model for the fillet weld stress. So conservative model basically how it does is you cut a 45 degree, which is essentially give you the throat area, right? So throat area, okay, when you cut a 45 degree at the fillet welds, and then we assume all the external force F will be acting as a shear force to that throat area. So it really doesn't matter how you apply the force, basically just saying let's explode the whole force F to the throat area here, acting as a shear force. Then the stress will be just a shear stress, which is F divided by the throat area, right? Or the total throat area, right? In case of you have a welding group. So this way you will get essentially a formula for the shear stress, which is just F over 0.707 HL, right? When you have just one fillet or one throat area. If you have 2 throat areas, then you time 2 at here. Okay, yeah. So that's the conservative model that we actually going to use for our case. Okay, yeah. So the next thing we're going to look at the 2 different cases, which I finished one case in the previous lecture. The first case is called in-plane torsion. So, and I want you to actually, clearly understand what in-plane is, which I will talk about the out-of-plane the next one, the case 2. So for in-plane basically means the F and the weld group, they are in the same plane. So you have weld group right here, you have the F over here. So these 2 are in the same plane. Okay, that's called in-plane right here. So when you apply F over here, and this is your weld group right here. Okay, you can have a 2 parallel line, you can have maybe a zigzag or that kind of things. Really doesn't matter how you weld it. It's called a weld group, right? Then this F will cause a shear force F at the weld group. At the same time, the F will cause a bending moment or torque, okay, on the weld group right here. So that two forces or torque will give us the total shear stress. So given this example right here, we have F, which will cause a so-called primary shear, and the F will cause a bending moment or torque, okay, around the centroid of the weld group. That M will cause a shear stress, okay. Even though this is a torque, or moment, in this case we're gonna all call it basically shear type of stress. So M times R divided by J will give us the second shear stress here. Okay, so that's basically primary and secondary shear stress. For the primary, it's just F divided by the total throat area. So this A here is the total throat area. And for the secondary tau double prime, okay, what we can do is, instead of calculate tau double prime, we calculate basically the component of tau double prime, the xy component. So we calculate these two components. So instead of m times r, so it'll go be m times a, and the other one m times b. And these two together give us all the components of the vector. So you see the tau x double prime is perpendicular to tau y, so tau y is in the same direction tau prime. So on the vertical side you have tau prime and tau y double prime, and then that's adding together squared and this, so you get basically the total shear stress. Okay, total shear stress. Now what about the G value here, right? The G, which is the polar moment of the area, second polar moment area. What we do is we use the table 9-1. So 9-1 give us the so-called unit second polar moment area, and it give us unit second moment area for a different type of well group geometry. Okay, so parallels, single, they kind of L or square. So you take a look at that table, you'll see a different basically geometry. The last column here give us the GU. So what we can do is we just use the GU times the 0.707h, which is the throat length. Okay, so that'll give us the total, basically the second polar moment area instead of just a unit. Okay, yeah, I'll give you examples after finish the case number 2. So that's basically for case number 1 when you have a in-plane torsion type of loading condition. Okay, for a welded joint. So let's take a look at second one here, which is the outer plane now. Okay. So case number 2, let's look at this so-called outer plane loading condition. Okay. Yeah. So I'll give you what the outer plane means at beginning here. Okay, let's say you have a wall at here or a plate. Now what we wanted to do is we have, let's see, a tube. Okay, we wanted to weld it onto the baseboard, a base plate at here. Okay, so here is the structure here. We wanted to weld the structure to the baseboard at here. Okay. How we're welding it, it's really up to the actual requirement. So you could weld it all around, or you could just weld the top or the bottom, or even just weld the two sides there, right? So that's up to the actual specification. Okay. But really doesn't matter how you weld. So if you can imagine here, so on this side you have this weld group, okay, the geometry of the weld here, and then you have the F over here. Okay, it's the loading force over there. Okay. Yeah. Okay. So if you look at this structure here, basically when you're talking about in-plane, outer plane, it's always the connection between the relationship between the weld group and the force. So if you look at this force at here, is over here, and the weld is over here and here, right? So basically if you look at the front, or if you look at the front view here, these two things, they are not in the same plane. That makes sense? Right? That's basically what we call the outer plane loading at here. Okay? Yeah. So if you look at the front view, you probably just see like this, right? Yeah. So this geometry is not in the same plane as F here. Okay? So let's call it the weld geometry and the F are not in the same plane. Okay. This is a distinct difference, right, from the case number 1 in here. Okay, yeah. So now you may have a basic, let's say, indication here. Okay, so here is my welding, and I'm welding it basically both sides, right? Using two triangles, both sides here with a leg height of h. Okay, that's the sort of symbol you would see for that type of welding. Okay. Now, let's take a look at the stress inside this type of welds, right? If I look at the front view, basically I see a fillet weld on the top, and then a fillet weld at the bottom here, okay, and then the force is applied over here. So over here for the welds, so what you see is basically you see basically a shear force F, right, all the way going down, okay, or going across the weld group. And at the same time, you will see also a torque generated by the F, which is basically times the total length L. Okay, right. So if this is the centroid, okay, of this weld group right here, so all you see is basically there's two type of loadings, right? One is the F, one is the M at here. Okay, so let me redraw this at here again. So then let's take a look at what type of stress will be caused by the two loadings at here. For the F, if I pick a point, okay, on the inside the weld group right here, which is basically inside the throat area, right? So you will see a shear stress, okay, which is the top, we call it tau prime right here. So that's this basically the primary shear due to the F right here. So tau prime is the so-called primary shear, which equal to F over the total throat area A. Okay, and then the second type of stress is caused by the moment or the torque at here. So if I pick this point in here, then there will be a shear stress pointing that way, okay, which is perpendicular to the basically radius. Okay, so this is called the secondary shear, and that's M times C over I at here. Okay, so this is different now. Okay, this is M times C over I. So M is this, and C is the distance from centroid to the location, right? Or basically half of the distance, right? Okay, and then I at here, right? This is the second, not the second polar moment area now. This is the second moment of the area, right? The second moment area. Okay. Now, why this is I but not J then, right? So you see the difference between when you see polar moment of area, it's basically you're trying to cause, if this is object, if this is the geometry of the object, you're trying to cause it to rotate, right? To rotate. That's G. But in this case here, this M is trying actually to cause what? Not the rotating, to bending it, right? If you have a shaft, right? If you have a shaft here, if it's a torque, then you're trying to cause it to rotate. But if it's a bending moment, then you're trying to bend the shaft, right? So this is basically I at here instead of a G, right? That's a very important difference. So when you see a question, you need to be able to identify whether it's in plane or out plane. Then you can identify the symbols, right? You know which tables you want to use. Okay. So and then this is actually easier for the case number 1. So my total shear force is basically vector addition, right, of these two together here, and you get your total shear stress. Okay. Yeah. So how do I find the I then, right? So to find the I, we use another table, 9-2. Okay, so 9-2 here. Okay. So this table is, show you what this table looks like. So this is just a part of the table here. Okay, so it's not the whole table there. And this is the table 9-2, part of that. As you can see, actually, there's a major difference. Basically, remember in polar moment area, you're not given both of the vertical and horizontal like geometry group like this, right? You're only given one of this vertical one, because horizontal, verticals, it doesn't matter for polar moment areas, cause rotation. But for the second moment area I, okay, you have these two distinct basically geometry group here. Basically what it means is, if you weld it like this, you have one I value. If you weld it like that, okay, then you have a different basically second moment area. Okay, you know, basically the bending will have a different type of results. Okay, so how you use this one here is find the geometry of this appropriately. So geometry basically means what the B is, what the D is, right? And then find the IU, okay? And then once you find the IU at here, then the I basically just equal to 7.707 H times this unit second moment of area. Okay, so that's how you can calculate the I based on this table 9-2 at here. Okay, yeah. So these two tables, 9-1 and 9-2, is essentially serving as the important information for the two different cases type of loadings. Okay, yeah. And also some of the parameter here. This one probably doesn't matter. But some of the geometries like X bar, Y bar could be useful when you do some calculations for the shear stress, but not this one. The case 1 it will be useful. Yeah. So it could be useful like this, right? So let's see the C value, right? The C value here, if you look at the C value at here, in this case half of D, in this case, okay, it's still half of D, right? Yeah, the C value. That makes sense? Yeah. So I'll give you an example once we finish the whole thing at here. So we'll take a look at a good part example together here once we finish the strings there. Okay. Any questions? So my expectation is, as I said, I give you an example. I expect you to be able to identify whether this is an in-plane or out-of-plane. And then you identify table 9-1 or 9-2 accordingly. Okay? Yeah. Okay, so now we are done with the stress. Let's take a look at the strains, right? The strains of welded joints. Okay, so for strains of welded joints, we're talking about the fillet type of welds. Okay, when you have a fillet type of weld, let's say you have a weld over here, right? Yeah. Now the location of interest could be at this location, or it could be at this location. Okay. So what the location basically I just draw here is the location at the joining location between the filler material and the base material. So that's called essentially attachment region or fusion area. Okay, so there are two different basically regions here. The first one here is called that attachment area, okay, or the fusion area, and the second one here is basically just in the weld itself. Okay, so classically, if you look at some of the textbook example, when you're talking about in weld itself, so what it really means is just for the welding material. Okay, because in the weld at here, it's like this is mostly the filler material or the electrode, right? So that's your electrode where you do the welding here. So that's where it really means for in the weld. And attachment area, that's the area where you have the molten metal, which is basically a combination or coalesce of the base metal and the feeder material, right? Yeah. So that's basically what this means here. But in my following examples, or in my expectations, okay, I'm going to consider the whole joints at here as a sort of a fusion area. Okay, so I'm going to consider everything over here is completely a combination of both the base metal and the feeder materials. Is okay? Yeah. So basically, when I consider strengths of welded joints, I consider the whole at here, and this whole thing at here is a combination of base metal or parent metal or parent material and feeder material, basically electrode. Okay, so that's what we're going to consider for a welded joint set here. Okay, so parent material we can definitely look up, okay, from tables the properties of the parent material. For the electrode at here, so we do need to use a table at here for electrode here. So first of all, the strengths for electrode. This is from table 9-3. Okay, table 9-3. Table 9-3, I'll show you what 9-3 looks like. Okay, so this is 9-3. And they give you different strength properties, okay, for different electrodes, okay, with a certain numbers. The first two numbers are the most important number that you should basically care about. 60 at here basically refer to the tensile strength, okay, which is SUT value. And the second column, the yield strength, which is SY value. It's just the first one is slightly different. 60 here is actually 62, but the rest of them are 70, 80, 90, 100, 120. You see the SUT, that's exactly the first two digits here, right? Okay. So that's electrode here. Okay, so from this given number, if I tell you use electrode 60, 10, whatever, and then you should know, okay, so that got to be a 62 or 60. Either number you've used, that's fine. Okay, yeah, I'll give you the SYT value. And this give you SUT. This give you SUT, and this give you SY value here. Okay. So basically, if I give you this, then you should know the SUT is 60 KSI. You use 62, that's fine too. Okay. And the SYT is 50 KSI. Okay. So that's what table 9-3 is. Okay. And then the next one here is we use a so-called welding code defined by the American, basically defined by the American Welding Society. So we have this so-called allowable, okay, stress by a weld code, okay, welding code. And this welding code is from table 9-4. Okay, so table 9-4 here. So let's take a look at this welding code, and then I'll explain how you can interpret this welding code here. Okay. This is the table 9-4. Okay. So for this table, how you use it is, okay, we're actually only using a portion of it, because as I said, my focus is on the fillet weld. So what we're using is essentially the last row at here. Okay, the last row. That's what the welding code for the fillet weld. Okay. So what it says is the permissible stress is a 0.3 SUT. Okay, that's permissible stress 0.3 SUT. Okay. On the footnote, there's another one here. Shear stress on base metal should not exceed 0.4 SY of the base metal. Okay? Yeah. Now, remember what I said when we look at the weld joint. So what we're looking at for the weld joint itself is we're going to look at it, consider it a correlate or combination of the parent material and the electrode, right? So it's a mixture of a few things. Okay. So when we do the calculation, right, what we're gonna do is we're gonna consider these two together. So here's what I'm saying here. I'll give you an example here. Okay. Basically, so for example, right? Let's see. Let's say we have welding. We're welding. Let's say maybe two metals. Okay. We're welding two metals together. So let's say there's one metal 1, and then there's another metal plate 2, and then you're using an electrode. Okay, so three things basically: one plate here, one plate there, and an electrode, trying to put them together. Okay, yeah. So for metal 1, you can look for the table, find SUT1, SY11, SY2, SYT. Right, so you can find the corresponding ultimate strains and the yield strains, right? And for electrode, and you can use the table 9-3, okay, to find the corresponding electrode SUT and SYT. So this is from table 9-3. Okay. Now once you list all of this together now, okay, then what we're gonna do is let's find what is the minimum SUT. So SUT1, SUT2, and SUT, let's call it 3 here, let's see, right? SUT3. So find the minimum SUT and also find the minimum SYT. Okay, so 3 materials, find the properties of each material separately, and then find the minimum SYT and SUT based on the 3 materials. Once we find the 2 minimum now, then we're going to use the welding code at here. So one is this 0.3 SUT, the other one is the 0.4 SYT. So what you do is basically you calculate the 0.3 times the SUT minimum, okay, and use 0.4 times this SYT minimum. So find the 2 things, okay, based on the welding code. Okay. Once you find these 2, and then find again the minimum value from these 2 numbers. So out of these 2 here, that will be our allowable shear stress. Okay, this will be our allowable shear stress for the welding joints, welded joints here. Okay. So you calculate the actual stress, right, based on the case 1 and the case 2. Okay. And then you calculate the allowable stress based on this scenario. Then you compare these 2. Then you'll be able to determine whether you have a safe condition or not. Okay. Yeah. So that's the process here. So you have a stress, you have a strength, and that's it. Okay. Yeah. Now for design, right? So basically, there are 2 different cases for analysis. Okay. For analysis, so it's the tau versus the tau allowable. Okay, so it's the actual stress versus the allowable stress. Then you get to determine whether you have safe or not. But for design, okay, then what happens is for design, so that here what we're designing is basically, for example, right, what is an appropriate leg height h. Okay, what is an appropriate leg height h, right, to satisfy this tau allowable. Okay. So that's a design type of question. In other words, if you think about back to the analysis at here, so when you calculate the tau is going to be a function of this leg height h, okay, leg height h, and then you let it equal to this tau allowable, and then solve for h, okay, solve for h. So that's what you can tell the welder. Go ahead, weld this joint with that geometry and this leg height at here. Okay, this leg height could be a quarter, could be a 3/8, whatever, right? So that's basically what you would tell the welder to do the joints. Okay. So that's basically the two different type of question at here for welding joints. Okay. I'll show you one type which is for the analysis, and then in the I'll post a couple other examples. One example will be the second one will be design type of question here. Okay. Any questions so far? All right. Okay, so let's take a look at the example and then put things together. Okay. So here are two plates at here. Too long. Let's make it a little shorter here. Okay, so plate 1, plate 2, and F is applied over here, and here's a welding symbol. Some dimensions are given. Okay, and the way we wanted to do it here is what? Here is this. There are two parts. I think there are two. No, just one part of the question here. Okay, find the allowable load F. Okay. If E70 10 for electrode is used. There are two base metal. Okay, one is HR 1020. The other is HR 1015. Okay, so let's try this example here. Okay, so first of all, as I said, you have to identify what cases this example actually belongs to, right? We have to do only two cases, in plane and out of plane. So what do you think? This is the in plane case or out of plane? What is it? In plane, right? Yeah. It's because the F. Actually, probably the first step you should do is when I have a welding symbol like this. So what does it really mean? So it means where's your welding here? Actually, here and here, right? Yeah. Okay. So that's basically what it means. So you look at the geometry of the weld and the force F. They're clearly in the same plane. So you're talking about basically in plane. Torsion type of loading condition at here. Okay. Yeah. So next thing what you do is you need to draw the welding group. Okay, appropriately. So this is, let's say this is a welding group for this example right here. and then label the dimensions here. So you have 2 over here and then 2 over here, right? Okay. So, and now the type of stress that existed on this question and here is basically you look at the point at the tape, you have tau prime, and then you have tau x double prime, and then tau y double prime. Okay, so that's the critical location basically, right? That's the critical location. So then I can calculate tau prime, which is f over the a at here, right? F over a. F we don't know yet. And a is the total, basically the total throat area. So if you look at the table 9-1, says A equal to 1.41, technically 1.414 times H times D, okay, times H times D. So D is the length, and H is the leg height. So if I talking about, let's see, what's the throat area for one side here, which is what? 0.707 H times L, right? L is the total length, okay? But L in this case is 2 at here. But because if you have 2, so that's why 2 times this give you 1.414, which is what inside that table there. Does that make sense? So if you can take a look at the other side table, let's say for example, if you take a look at this one here, right? What's the total area? So 1.414 times H times B, and the other one 1.41 times H times D, right? So 2B and 2D. So you got a total throat area. Okay? Yeah. So this side here, remember, this is the total throat area. Okay, so go back to here. So A at here should be so from table A-1, so A equal to H times or B times 2 basically. Okay. Yeah. So I think the other thing you have to be very careful is, actually this is one time I tested. Instead of a 2 and a 2, exactly the same shape, then I use a 2 and a 3 at here. And that threw many people off. Okay. So if I use a 3 at here, what should you time? Time 2 or times 3? 3, right? Yeah. So I know a lot of people trying to remember things, but you got to understand what this means basically. Okay. Yeah. So A equal to this, and then I can calculate tau prime, which we can't yet, but we don't know what F is, right? So H is well, let's just keep it here. So H equal to 5/16, right? That's your H. Okay. Yeah. And then we can calculate tau x double prime. Okay, tau x double prime. So tau x double prime equal to what? Equal to m times. So maybe I should label this correctly here. So this is a D equal to this, and a B equal to 2. Okay, according to table 9-1. So if I calculate tau x double prime, that should be m times. Sorry, what's B and a D again? Just give me a second here. So D is this, yeah. So if I calculate tau x double prime, what should I use? M times what? And then divided by J, right? So what should I use at here? M times B over 2, right? B over 2. So that's how you generate tau x double prime. Okay. And then your tau y double prime should be m times D over 2 over J, right? This is, sorry, yeah, you got a question? So this is how you actually, this is right? So you see that's B, that's D, right? Yeah, I want to make sure that. Okay. Yeah. Okay. So what about the G value here, right? So G value from the table is here. So this is your G value, the GU value. But we multiply this value with 0.70 H to this point here. Okay. Yeah. So 0.707 H times GU, and GU equal to D times 3B squared D squared over 6. Okay, over 6. Now this is exactly my point here. See this formula, right, inside this table 9-1, it's all about the B and the D. Okay, B and the D. So if you got your B and the D mixed up, then your GU will be wrong, right? If your GU is wrong, then the rest of the calculation is all wrong, basically. Okay, yeah. So that's where you have to be very careful in terms of dimensions. Okay, yeah. So I can substitute the into here and here. What about M? So M equal to what? F times how much of a distance in this case? The M is about which location? The centroid, right? So times how much? 7. Okay, so 7F at here, and then I can plug in everything into tau x prime, tau y double prime. Then we can calculate our combined shear stress, which is yeah. Okay. Yeah. Oh, I guess my notation wise, sometimes if I use the horizontal is x-axis, right? I label this as that. If I use vertical x-axis, then it, right? It's just a simple difference. Okay. Yeah. So this totally will give us 9.22 times F. Okay. So that's the shear stress due to the loading force F. Okay. Okay, so then finally we need to calculate what is the tau allowable. Okay. And then I can compare the tau allowable with the tau at here. So we have 3 different materials. One is 1020, the other 1015, and last one is a electrode 7010. So I can look up a table from the appendix, find 1020 SUT is 55 KSI, and SYT is 30 KSI. For 1015, okay, and electrode E70, you got a 70 KSI here, and SYT is 57 KSI. Okay. And this is from table 9-3. Okay. So the properties of the 3 different materials are listed over here. Then I can calculate allowable shear stress as the minimum between the 0.3 SUT minimum and 0.4 SYT minimum. Okay. So as you can clearly see, what are we calculating? We're calculating 0.3 times 50 and 0.4 times 27. Okay. This is 27.5. Okay. So these two numbers, this is give you 15 at here, this give you about 11 at here. So overall you get 11 KSI. Okay. So that'll be our allowable shear stress at this joint. So last step is compare this allowable one with the actual shear stress. So we let tau equal to tau allowable. Then we can derive an expression for the force, which is 1.19. So this is KSI here, okay? So your results you get is a 1,000-pound force, okay? So 1.19 kip. That's overall idea for this kind of a design for the welded joints here, okay? So the expectation is very clear. Look at the question, identify whether it's in plane, out of plane, and then calculate the total stress. Okay, really doesn't matter what type of question you're being asked for. You're gonna try to calculate the total shear stress at here, right? And based on the geometries, based on the given force. If force is not given, then just keep it. If force is given, but leg height is not given, let's see if this h is not given, then you keep the h, right, as a variable here. Okay. And then calculate the allowable shear stress like this right here. And you compare these two, and you solve for the unknown quantity. Okay. Any questions? Okay. Okay. Good. So, if you don't have any question, then I'm going to move on to the spring now, which is the last part of the lecture now. Okay, of the course. So spring is actually a very common machine elements. You probably will see that many applications in the automobile. Okay? And we all have our spring damper system in our car. And the quality of that spring damper system actually really means how comfortable that you're driving, right? Yeah. And one of the things that you probably notice if you have been driving your car for 20 years or 30 years, and it becomes much more bumpy, isn't it? Right? Yeah. So that all have something to do with the property of the spring set here. So what we wanted to do is we want to basically normally we want to design a spring to satisfy certain loading conditions, okay, like what I showed here. Now, the focus on this part of the lecture is we're going to focus on the compression type of spring. Okay. There are springs applications for tension type of application. There's also springs for torsional type of application. Okay. So what I'm going to focus here is on the compression application. Okay. But the structure of the spring, especially helical spring, you know, it's applicable to both compression and tension. Okay, but my further calculation in here will be on the compression only. Okay, so let's take a look at some of the key parameters for spring. Okay. Spring is essentially like the helix, the thread form, right, on a screw. It's essentially a helical curve. Okay. The mathematical formula is basically helical curve. Then the important parameters is the so-called coil pitch. Okay, so that's the distance from center to another center, adjacent center, okay, along the wire. There's also the wire diameter, which is also very important parameter. So that's your wire diameter here. Okay, and that's basically how you build your spring. When you build a spring, you need all the material, and we build our springs using some special type of wire. So, and the wire has certain diameter, so that's basically how your spring is formed. Helix angle phi, that's basically horizontal angle between the helix and horizontal lines. Okay, so helix phi. Mean coil diameter, capital D. So that's the diameter from one end, okay, to the other end. So it's from the one end of center to the center of the other end. Okay, that's the coil, mean coil diameter here. Okay. Now There's another diameter, and often in time it's also useful, which is the so-called outer diameter. So OD at here. Okay. So geometry-wise, what's the connection between the outer diameter and the mean diameter and the wire diameter? So D and this, what do you do? Add them together, right? Yeah. Okay. So your mean diameter equal to outer diameter plus the wire diameter. Okay. So another important thing is actually it's called the total number of coil. So this is actually one thing I find very strange. Many of us don't know how to count the total number of coil. How do you count the total number of coil? What counts as a one coil? How many degrees? 360 degree counts, right? So if you start at one location, you start to go 360 degree. When you come back, that's one turn, right? Or one coil. Okay? Yeah. So let's see if I count it like this one here. How many coils do I have? From here up to here, that's 1, 2, 3, 4, 5, 6, 7, and then how much is this? Half, right? Huh? I started here, right? Yeah. So this one here, for this one is 7.5, which is NT at here. Okay, which is NT. That's how you count the total number of coil. Because unfortunately, no matter how much I emphasize this, every time when I test the question in the final exam, there are a huge number of students just give me a completely different total number coil. And guess what? You get that number wrong, the rest of the calculations is all wrong, right? That's unfortunate things. So I've always struggled whether I should give you the total number coil or you count it by yourself. But I always think this is a super easy one here, right? Yeah. So for those of you here, are you clear with how to count the number of coil? Good? Okay, good. So that's NT value, okay? There's another one called active number of coil. Now this one is different from the total number of coil, okay? Yeah, could be the same. Because as I'm going to show you, not like this one. This is called a plain spring. Basically, there's no process done, so whatever the original shape of the helical curve is, then it's kept as it is. But for spring, sometimes what we do is we do some processing to the end of the spring or to the end coil of the spring. As I'm going to show you, basically we either close it or we ground it. Okay, so the ending at here or here will not be always the same like this one here. So that'll give you a completely different, actually, the so-called active number of coil, NA. Okay, so I'll show you how to calculate this. So this NA really depends on how the coil is ended, which is given by this parameter NE. So there's a connection between this. So in general, okay, in general, these two are not the same. There's only one condition when this is 0. Like this one here is the same. The NA is the same as NT, but in general, they're not quite the same. Okay. Yeah. Free length basically means if you don't press it and how long the spring it is. Okay, when it's fully standing there. Solid length basically when you completely close it. Close it means there's no gap between any two adjacent coil. So you apply certain force, complete close it, okay, without any further deformation. Then that gives you the so-called the solid length LS. Okay, yeah. So those are some very important parameters for further calculation of the springs that are here. So let's take a look at what do we mean by the different ending for the coil at here. Okay, and how does that relate to the number of active coil. Okay. So let's take a look at this one here. So this table 10-1, okay, is actually the basically the type of ending here. So table 10-1. There are 4 different types. Okay, plane. So the plane is this one here. So this is a plane ending. Right? There's no additional process down to the ending of the spring here. Another one is called the plane and ground, square and or closed, or square and ground. So what is the difference between this one here? I'll show you the picture here. If this is the plane here, and this is basically the square or closed here. So square or closed. So you can clearly see the difference, right? So basically, the last coil, right, or the ending of the coil are being pressed, okay, and touching the adjacent coil basically. Okay, so there's no gap here anymore. Okay, so that's called a squared. And the grounded basically means if this is the plain one here, right? Not like this. You don't square it. So all you do is you just ground the top portion, okay, and make it flat. So that's what ground means here. Okay. Yeah. And ground and a square basically means you squared it first and then you ground it. Right? So that's ground and a square. Okay. And this diagram here shows you a ground and square type of spring. Okay. So when you have a ground type of surface here, and it's basically flat, so it can distribute the force much more evenly, right, to take all the external force. Okay, so this is a very common type of a coil, right, ground and square. Now, because of this process, right, because the process for these two at here, so you will lose half turn for both ends. Half turn here, half turn here, half turn here, half turn here. So as you can see, right, the total number of coil is equal to NA plus 1. So basically means that for this one here, NA equal to what? NT minus 1, right? NT minus 1. So the active number of coil is the total number of coil minus what? Give you the active number of coil. That makes sense? Yeah. So if you count the total number of coil, it's still the same way as you count it, right? So starting from here, like each count it, and then minus 1, that'll give you the active number of coil. If you have a ground and squared, then the active number of coil is NT minus 2. So basically what happens here is you're losing 1 turn at both ends for ground and squared. So the active number of coil, the total active number of coil is equal to the NT minus 2. Okay? Yeah. So that's the connection. And the other information from the table is also useful, is you can calculate the free length and the solid length using the formulas given at here. Okay, so this table 10-1 is very useful, okay, when you calculate those parameters, which you will need that for further calculation. Is that cool? Yeah? Good. So let's take a look at an example here, right? Let's take an example, and I want you to let's maybe just take a look at this example here. This is the squared one here, okay? And I'll give you, for example, I'll give you P equal to 5 millimeter and D equal to 3 millimeter. Okay. So I want you to do it yourself here. What's NT? What's NA? And what's LO? And what is LS? Basically the free length and the solid length. Okay. Try to count it. Okay. So this one kind of tells you already. This is a square, right? And this is a key keywords here. It's a squared. So basically that'll tell you how to calculate the NA next in the next step. But first thing, how many number of coil in this spring? Yeah, got it? Okay. How many say it's 7? Nobody? How many say it was 8? Good. Very good. Okay, so it's 8, right? Starting here, so one turn is 1, 2, 3, 4, 5, 6, 7, 8. Okay? Yeah. If it's 8 for NT and it's squared, so looking at table 10-1, what do you think the total active number coil is? Which column are we talking about here? This one, right? Yeah. So NA equal to six. Okay. Yeah. So that's squared. And now, in terms of LO and LS, you can directly calculate based on the formula from 10-1, and that's the two formulas from 10-1. Okay, so LO and LS. Okay, and then plugging all the numbers. Okay, you get 39 at here millimeter, and then 27 millimeter. Okay. Yeah. Okay, so that's your spring at here. Okay. Yeah. Okay, so just like every other machine component, so what we need to do for analysis is we need to come up with the stress expression for the component. We also need to come up with the strength information for that component. Then we can basically compare it with each other. So let's take a look at the next one. How do we calculate the stress in the spring? Okay. So I draw the spring, and here I actually draw the cutout illustration of the spring. So let's suppose if you have a spring like this and then acting force on the top of each other, and if you cut it out in the middle anywhere like this, and then we look at the cross section and here. So that's basically the free body diagram for this portion of the spring at here, right? Yeah. So if I look at the cross section over here, right? If I look at the cross section here. Now look at the cross section. So then, technically speaking, I would have a force, okay, going down to the cross section, right, by this force at here. So that force will acting on this cross section, and then there's a torque going this way at here. Okay, basically the opposite of the free body diagram. Right, free body diagram. This is basically the action-reaction, right, to balance out this F. And what I draw here is the force and the torque caused by the F at this location, at this cross-section area. Okay, and this force is equal to F times the distance here, which is basically half of the mean diameter, capital D. Okay, so that's your torque. So you got two basically two different forces. Actually, I should no, I should stick to this drawing here. Sorry, maybe I should stick to the drawing here. That doesn't make sense. Yeah, let's stick to the drawing here. Okay. Okay. So. Okay, so then each one of these, right, will cause a stress, okay, along this shear, along the cross section in here. Spring cross section are typically very small cross section, so you can consider the F as sort of a direct shear. So you can consider it's a direct shear at here, okay, on the cross section. So direct shear basically means we got a force divided by the area. Okay, that gives us a direct shear, and area is pi times small d squared over 4, right? So pi times r squared, and r equal to d over 2. So you get this, which is 4f over pi d squared. Okay, and the torque will also cause a shear stress. So that's the torsional shear. And this is, let's call it tau t at here. So this is t times r over j, okay, formula wise. Okay. R basically is R is basically the half of the wire diameter, so which is a small d over 2. And the torque, as we just derived there, is F times d over 2. And G is the second polar moment of this cross area, so which is pi d 4 over 64, right? 64 or 32? 32. Okay. So this one can be simplified to be 8fd over pi d cubed. Okay. So if you look at this one and here, now which location actually has the maximum shear stress on this cross section? The direct shear is evenly distributed, right, along this cross section. The torsional shear is basically going across the edges, okay, at this cross section. So as you can see, when do we add these two up? At which location? Along the cross section here on the edge, over here, right? If at this location we add the two shear stresses up, okay? So that basically gives us a maximum tau, which is these two addition here. Okay, so that gives us this one here. Okay. And then these two equations can be simplified, okay, to be the following expression here. Can we spread this? And the key asset here is basically called 2c plus 1 over c, and the c is the ratio between capital D and small d. Yeah. And Ks has a name for it. This is also called shear stress correction factor. Yeah, because you can see it, this is the same as the torsional shear, right? This portion. Okay, then you time Ks, you get a total shear stress. Okay. Yeah. So that's theoretical calculation of the shear stress, okay, at the cross section, any cross section of the spring, okay, under loading force F. Okay. So that's how you get it. Okay. Now. But in reality, see, this is basically what I showed you here, right? But in reality, then what happens is, when we do the calculation, we're as like considering the spring as if it's a straight wire, basically, right? But spring is not a straight wire. Spring is a curved wire. And for curved wire, the experiment shows that the inside, okay, and it always actually have a relatively bigger stress value than the outside here, okay? So then what happens is, what we do is we use experimental results, basically very much like the results we just derived here, except that a stress correction factor, Ks. So now we use a so-called Kb at here. Okay, Kb. Kb is it's named after a guy called Berg-Strasser factor. Yeah, so it's named after this one of the person here. So KB, okay, is equal to 4C plus 2 and over 4C minus 3. Okay, so that's a slight difference here. Okay, the KB is called Berg-Strasser factor. So basically, we're going to calculate our stress for the spring, okay, using this formula now in the next few steps. Okay, yeah. Was that good? Yeah. Okay, so this is the stress. Okay. And there's one more thing in here, and then we'll talk about strains. Maybe we'll just stop it here after this one more here. And the other one is, okay, we're talking about strain, then there's definitely force and deflection. And how are we going to calculate the spring stiffness? Okay, spring stiffness. So when you have a force and deflection, and then you will have a spring stiffness, so which is the K here. Okay, so K equal to what? Spring stiffness. Now this one here, I'm going to skip something. You're going to have to use so-called Constigliano's theory. Okay, you can take a look at the textbook. The textbook probably have a shortened version of the Constigliano theory. Essentially, it's energy type of theory. Typically in mechanics of material 2, and you'll learn this theory. How to calculate the K here. Okay, so but either way, K equal to F over Y. Okay, from this theory, we can derive the deflection. Okay, is approximately equal to 8F d cubed times NA, and divided by d to the power 4 times G. Okay, so what are each one of the symbols here? F is the force. Capital D is the mean diameter of the spring. Okay. Small d is the wire diameter. Capital G is what? Is the shear modulus, right? There's Young's modulus E, and this is the shear modular G. Okay. Yeah. This one you can find it for different spring material. Can find it the G value, and I'll tell you how to find it. NA, what's NA? If you just recall that, the total number of active coils. This is another thing that threw many people off at it here. When you calculate this one here, you need to use the NA, not the total number of coil. It's the total number of active coil. Okay. So then I can derive the K from here equal to d to the power 4 times G, and over 8 to the power of 3, d to the power 3 times NA. Okay? So that's basically the calculation of the spring stiffness formula. Okay. So up to now, we pretty much got all the parameters spring figured out, right? Basically the total number coil, total number active coil, free lengths, solid lengths, spring stiffness, right? And then in the next lecture, I'll quickly go over the strains and I'll give you an example for spring design, and that's it. Okay? Yeah. Any questions? Good.